Okay, here we are. Hello, everybody, and welcome to VascageNet Webinar number 5. Sorry. Hello, everybody, and welcome to VascageNet Webinar number 5. My name is Andrea Guala, and I'm Vice Leader of Working Group 5 and leader of the training activities, among them this series of webinars in the European Cross-Action VascageNet. VascageNet is a network of researchers from Europe, the US, and Australia who are working together to refine, harmonize, and promote the use of vascular aging measures in order to improve clinical practice and reduce the burden of cardiovascular disease globally. Before we get started, I would like to run over a few housekeeping points. Firstly, your Microsoft should be muted. If not, please make sure it is now. Secondly, the webinar is being live streamed on YouTube and will be recorded and shared on our website following the webinar. To ask a question at the end of the webinar, please type it in the question and answer box, and I will make sure Prof. Oscar Camara will receive it. And finally, we will not be able to assist you with any technical difficulties throughout the webinar. So it is my great pleasure to host this webinar and to introduce our speaker, Professor Oscar Camara. He is an associate professor in the Department of Engineering and Information and Communication Technologies at the University Pompeu Fabra in Barcelona, Spain. He obtained a PhD in image processing in the École Nationale Supérieure de Télécommunications in Paris, and that postdoctoral stay at King's College London and University College London. In 2011, he founded and since then coordinates a research group called FISense at UPF, where he is also coordinator of the biomedical engineering degree. His research is focused on computational imaging, computational modeling, and artificial intelligence for clinical environments, including cardiology applications. He is actively involved in competitive national and European research projects, including strong collaboration with industrial and clinical partners. So today, Professor Camara will be speaking to us on artificial intelligence for the investigation of vascular aging. Dear Professor Camara, thank you very much for taking the time to speak with us today. I will now hand over to you. You can share your screen and start the presentation.
Thank you very much, Andrea. Can you see my screen now?
Yes, if you go full screen, it will be okay. Thank you.
Okay. Well, thank you very much for the introduction and for the invitation to give this webinar. I'm going to start right away. Andrea has already introduced myself. I'm a full professor at Universitat Pompeu Fabra, and during all my career, I've been working in different computational techniques for data processing and computational modeling in several medical applications, including cardiology, neurology, and oncology. So I've been involved in quite different multidisciplinary aspects and in different disciplines. So I have a research group at Universitat Pompeu Fabra, FISense, but we are part of a larger research unit called Barcelona MedTech with other research groups where basically we touch a lot of different aspects of biomedical engineering, always with a high interdisciplinary and translational philosophy behind, and including a lot of different techniques like data analysis, biomechanics, electronics, etc., and obviously including machine learning. So kind of the first disclosure is that I don't really consider myself like an expert on AI and machine learning, but nevertheless, this is the fourth invited talk that I give in a year in kind of clinical forums or research forums on AI for fetal cardiology, for cardiac surgery, and now for vascular aging. And in fact, the other thing is that for sure I'm not an expert on vascular aging per se, like most of the participants in this cost network. Again, however, for the last 20 years, I've been working a lot on different cardiovascular applications, including image and signal processing for electromechanical model in cardiac arrhythmias, the study with simulations of hemodynamics in cerebral aneurysms, in left atrial appendages, and also more and more on fetal circulation, developing lab models for fetal circulation, and studying heart-brain connection. And in fact, as I've been working on brain applications and heart applications, 5 years ago, I was trying to get an ERC grant. And obviously, I mean, if you want to put together the brain and the heart, there is something in the middle. And in fact, this is how I entitled my project, like you need to go through vascular territories on this journey to study the heart-brain axis. And basically, it was just to find ways and innovative ideas to have a more systemic and holistic approach to study together the brain and the heart. And the first idea that I'll show you some results later was to relate, I mean, a stroke and atrial fibrillation. And the second idea was more to work on data of young people, babies even, to study the influence of cardiovascular abnormalities in brain development. And this is very interesting, in particular with babies that are born with low weight because of some problems in the placenta of the mothers and what is called intrauterine growth restriction. And in fact, this disease affects both the brain and the heart. And in fact, in the brain, we could see that the ageir babies have less volume than normal, but surprisingly, they have more folding than normal. And folding usually is related to cognitive characteristics. So, and this is quite strange because in the cognitive test, the ageir patients perform worse. At the same time, there are vascular remodeling in these babies in the fetal circulation. And in fact, the whole circulatory system remodels to protect the brain of the babies. So the idea behind this project was, in a sense, to prove that hemodynamic and vascular changes in these babies had an influence on brain development and how to relate it. So the thing is, the first stage of this project was quite nice. I was invited to defend it in Brussels, but the problem is that in the second phase, I mean, they pissed on me a bit. Like they say that, well, I had 12 reviewers and contradictory information. In the end, it wasn't given, but they told me to apply again the next year. But the next year I failed again. I mean, for whatever reasons. But it's okay. I mean, in the end, this exercise of brainstorming helped me a lot to set up very interesting projects that I'm now involved. So I really recommend young researchers not to give up, be resilient about your ideas and go ahead even if you have bad results at the beginning. But let's focus a bit on vascular aging. That's the focus of the webinar. So there is a really nice recent paper by Unvari and colleagues, where it's reviewed all the important factors, circulating, non-circulating factors, multi-scale factors that can lead to problems in vascular aging and functional dysregulation, that it ends up with some manifestation, pathophysiological manifestations like hypertension, like aneurysms, cognitive issues like Alzheimer's disease, hemorrhages, or the presence of plaques or thrombus that can develop to stroke or the different types of manifestations that to some extent, these are the consequences that we can check with data that can be acquired. In another recent paper by Segers and colleagues also, I mean, you know perfectly how it's important to measure arterial stiffness for vascular aging, and all the different techniques that are available for the estimation of the surrogate of arterial stiffness, pulse wave velocities, with imaging, with signals from tonometer ultrasound, from cuffs, etc. So this is a lot of data that can be acquired to have surrogates of arterial stiffness and vascular aging. And in the end, like a lot of different problems in cardiology, we can end up with big data for every patient and even larger data, a deluge of data for population in population-based statistics. So it's a lot of information that is generated that needs to be interpreted for research, for investigation, but also for clinical decision. And in fact, in the end, we want to we have the patient, we have all this data, and we need to work together, clinicians and engineers and biologists and other scientists to find more and understand better these pathophysiological mechanisms and make better clinical decisions. What we can do with all this data, but basically we can process the data to extract indices of function, of a structure, geometry, shape, deformation. We can integrate the data because in the end, each sensor will offer complementary data or information with different resolutions and incomplete each one. We need to create reference systems to integrate all this data. And obviously, we can try to model with physiological models or data-driven models to better understand what is going on and trying to predict what is going to happen after some actions. Can artificial intelligence and machine learning help on all this? Well, I mean, yes, the short answer is yes. In the end, everyone knows what to do with this data in terms of classical statistics from large data sets with population information, with basic tests like t-tests, etc., ANOVAs, etc. Machine learning is kind of an advanced way of doing statistics, and basically it has the ability to learn from data without being explicitly programmed. But what is important is that the problem is well posed, well defined. I mean, we need to be conscious that the machine is not going to think for us. And it needs to be, it's very important to have a very well-defined task with a very well-defined metrics that we are going to measure the accuracy of the algorithm. And we need to have a good database to learn from. Let's review a bit some of the machine learning basics. And why we are talking so much now about AI and everyone wants to know more about it. AI is nothing new. From the 50s, there were the initial developments on these technologies. And in fact, during this kind of 50, 60, 70 years, there has been a lot of winters and summers, what it's called, where, I mean, it looked like this technology was going to solve everything, but in the end, it was a bit too much hype and not fulfilling the expectations. And now we are living kind of a new summer of AI and machine learning. And it's because what had happened around 2012. And what had happened in 2012 is that Google released or had released a large database of natural images. And they set up a contest. Well, there was a contest called ImageNet. And in 2012, some researchers developed some deep learning methods, some based on neural networks, CNNs, that provided very, very good results comparing to the state of the art before this point, improving the accuracy over 65%. And this was quite a revolution. And in fact, after 2012, these techniques have been improving and improving to reach levels better than human skills for this same task, but basically just to recognize objects in these natural images. People involved from the very beginning in these developments, they are now rock stars. like these four. They are very well-known influencers on these topics, and a lot of them are working part-time in Facebook, in Google, etc., or Andrew G. that in Stanford, that his courses are followed by hundreds of students every year. But in fact, there was nothing super extremely new. Basically, there was a conjunction of different things, basically three aspects. One, to have access to well-curated big data, digitalized and access openly to researchers. There were some developments in computation, basically to have more access to supercomputing clusters, to HPC, high performance computing, to graphical cards to have and to train these models. And also there were some, obviously, algorithm progress, like advanced deep learning, etc. So all these things together make kind of this hype appear and the application for new fields. And obviously medicine was a field where artificial intelligence started to have an impact. The problem also it was that it began to appear in some covers, a bit sensationalist headlines like artificial intelligence is going to replace doctors. And obviously this is far from what is going to happen. And what is happening, what is true is that clinicians and researchers like us, we need to be aware of these techniques, and probably people not being aware of these techniques will be a bit out of date in some years. In the end, again, from the simplest machine learning algorithms, basically we need a database of label data. And to generate these labels is sometimes the hardest part, because usually it needs to be done manually by humans. And if the database is large, this can be really a manual and tedious process. And basically in the machine learning algorithm during the training phase, what is learned is the relation between the original data and the given label. To predict this label in an unseen data. And this is the phase of the testing or the prediction. So when new data is coming, if it's applied to the learned model, it can predict the label on this data. In an example with medical images, well, we can have ultrasound images of a healthy athlete or an hypertrophic cardiomyopathy, and then the task is just to discriminate between physiologic or pathologic LV hypertrophy. And then basically what it's going to do, the algorithm is when a new image is coming, is going to tell if an image corresponds to each one of the classes. It's important to differentiate between these basic machine learning algorithms that are called supervised learning, that they need this label training set, or unsupervised learning, that labels are not needed. And this is quite useful to discover patterns, to extract new knowledge from the unlabeled data. There is also other things like reinforcement learning that I'm not going to enter in detail here. And basically here we can have an example. Again, we have some images of gallbladder, and basically the human is saying this image corresponds to gallbladder and this one also. And the computer relates this image with this label, gallbladder. And then when unlabeled data comes here, the algorithm has learned this function between image and gallbladder. And then with this new image can differentiate between these two classes. Unsupervised learning is different in the sense that we don't give this label. We give a set of different images to the computer, and then the algorithm generates different clusters. And the important thing of supervised and unsupervised learning is this regression and interpretation of the clusters by the human, because then we can identify what's different in the two clusters. And the human and expert can say, okay, well, these images were of bleeding, and these images were without bleeding. And this can help to better understand the data we are dealing with. Usually, the classical methods, not even machine learning, in the end, the solutions were handcrafted. Basically, we were processing the data and we didn't need a training phase. In the classical machine learnings, the humans were picking some features, some characteristics from the data, and then we were using classical shallow methods for classification. And deep learning, like convolutional neural networks, what is interesting is that the user doesn't impose which features we are going to use in the process. It's the algorithm itself that selects the best features for the given task. And in fact, there is a lot of different algorithms, both in the shallow region, the more classical and old style machine learning, or on the deep learning techniques. And in the classical ML techniques, and maybe people are more familiarized, here includes classical K-nearest network, rule-based techniques, decision trees, random forest, support vector machines, linear discriminant analysis. And these techniques, even if they are older, they are still very useful. And it's up to the user to really choose between one technique or another. In terms of the deep learning, and deep learning, in particular, neural networks works very well with imaging. Basically, what it does, it just from the original image, we apply a lot of different filters. It's kind of multi-scale and multi-resolution analysis of the images. And the analogy with neural networks is because the brain does this also, kind of analyzing different parts of the image by different parts of the brain to extract different features that in the end, they will be combined. In the end, there are some weights in these transformations that these are what is optimized in the network, so that by the combination of these weights, it relates the original image with the label, in this case, a cat. Okay, so it's a hierarchy of different layers that transform the input data into more abstract representations of the image. And in fact, we can see from whatever natural images and the filters that have been performed on the images, while at the earliest stages, we see that the machine or the algorithm identified edges, then noses, and then faces. And in the end, all this is combined just to see for which level is the good one. There is a huge amount of different possibilities in neural networks. This is a nice scheme provided recently. And in fact, this can be a problem because it's kind of an agony of choice, because you can choose about different architectures, metrics to define the accuracy, how you sample the data, how you optimize the whole process, how you normalize the data, how you pre-process, how you post-process the data. And this is a bit the black magic. Is how you perform this, you will obtain some results or others. We are lucky that there are some tools that they are very robust in a lot of different applications, like this UNet for medical imaging that is used in a lot of different contexts, and it works very well. This was developed by Ronneberg, and basically when when you have a problem in relation basically with medical imaging, the first thing you need to try is the UNet, or some variations like the no new UNet that is very useful and quite robust for different problems. Okay. Some, let's say, different type of neural networks. It's what is called generative adversarial network, GANs, that is kind of also an epidemic by the amount of papers that we have seen, and the principles are a bit different. In this case, we have kind of two networks. One is the generator and one is the discriminator. And to the what we do is kind of the generator needs to learn to fake the discriminator. And how it's learned is that at the beginning, you can input to the generator whatever, it can be noise. And with a lot of different iterations, so the generator generates a sample, and the discriminator, what it does is to compare real world samples so real images, with the sample generated by the generator. And it says, okay, so this is fake or it's real, right? And with different iterations, the generator is learning by the error, the loss that you have in here between real and fake, is learning on how to generate images that are closer to real images. And in fact, this is a really nice analogy. It's like whatever a thief is trying to give to a police, whatever, some fake money, and at the beginning it's not really nice. It's kind of, look, it's not even green. Then it switched to green. Hey, but there is no watermark. And with different process, I mean, let's say the thief, the generator is learning to, when we reach a point that the discriminator doesn't recognize if it's fake or real. And obviously, this is super interesting because you are learning the characteristics of the real data. And this can be useful for a lot of different things, like basically synthesis in biomedical imaging is used to generate a CT image from MR, etc., etc. So this is a new class that is becoming to be quite nice and applied in a lot of different applications. But let's see more on AI in healthcare. So when we look at the pipeline in the clinic, in particular for data analysis, we see that we can divide in four different boxes. We need to acquire the data, we need to extract features from the data, and then we need to interpret all this data and probably classify the data or phenotyping, and then make decisions and just support this decision with computational techniques. Obviously, when we go in this axis from the left to the right, there is an increasing risk for patients depending on which are the decisions. And what we can see is that until now, most deep learning techniques has been applying on the two left side boxes, like on data acquisition and on feature extraction, because there is a less risk for patients. And also because a lot of these deep learning, in particular deep learning techniques, they behave like black boxes. We are not very sure what is happening inside. And obviously you cannot use this type of algorithms, or you need to be very careful to use black boxes for interpretation of the data and also for decision support, where you need more reasoning and it needs to be explainable, it needs to be interpretable, the outputs of the algorithms. When we see a bit more in depth the different stages, in this case for cardiac imaging, despite these issues, there is already impact of AI on all these different stages. Even from the very beginning contact between physician and patient, there are natural language processing techniques to improve well, the communication, or even at the other side of the spectrum to automatize reporting. And in the middle, for what I was saying, cardiac image acquisition, pre-processing, post-processing of the data. And obviously, to improve time efficiency, to improve reproducibility, standardization, and save time from clinicians for labile tedious tasks. This is just an example for cardiac surgery. Again, it is similar what I was saying. Integration of data, multimodal data that we can have from the electronic health records, from imaging, even genetics, to provide a risk score, even during the intervention, to process the data acquired, to integrate with preoperative data, to also compare with population data statistics, also to for the follow-up, to integrate data from multiple wearables, etc., etc. Let's see a bit different steps, some codes of machine learning and artificial intelligence in all these different steps, starting for cardiovascular imaging and signals. So this is a wordle that I did recently from the largest conference annually that we have in medical imaging, MICAI. And in fact, you can see from the last, let's say, 5 years, almost everything is about deep learning. Deep learning, neural networks, and basically these are the main concepts, and they are applied on any medical application you can imagine. I mean, there are no more low-hanging fruits on applying deep learning for basically biomedical engineering. Some aspects are on the image reconstruction. This is just one example. On cardiac MRI, probably you know, most of you, how generating an image is kind of slow. It takes time. And the group of Daniel Rucker in London, now in Munich, they have been working just to accelerate this image reconstruction with kind of classical, typical deep learning techniques. And basically, they manage from kind of 6 times undersample K space, so kind of 6 times faster, they can generate medical images, MR images that are kind of similar to the ground truth. And obviously, if this can accelerate 6-fold the reconstruction of the image, this can have a very important impact on the clinical workflow. Other type of applications are quite, let's say, widespread these days is just on feature extraction. But again, very important is just to have these labels, this large database with manual labels. And this is a very good example on the UK Biobank dataset, where Stephen Peterson managed to have some people for 1 year segmenting manually more than 5,000 MRs, where they were segmented the 4 chambers of the heart. And after this, just basically train some neural networks. And this is what companies like Circle, they are using just to provide a fully automatic segmentation of the 4 chambers of the heart right now in a commercial product. But obviously you needed some people to be 1 year segmenting manually this large database. Here we have been using similar techniques, handling with database a bit smaller, like in this work to process medical images of placenta, to segment, and then to help clinicians for fetal surgery, like in this case, that they need to ablate the vasculature in twin-to-twin transfusion syndrome patients that they need. I mean, they have 2 babies and they need to ablate some vessels between both of them. Also, we have been applying these techniques, CNNs, for the detection and segmentation of abdominal aortic thrombus in postoperative CTAs that we can just see here. But basically, it's just with this type of techniques and dealing with a small amount of cases. Other researchers are applying this also for device selection, like extracting automatically some features from the images, in this case CTs of the aorta, in order to predict which is the optimal, in this case, valve replacement for a given patient. It was an Edwards-Tabby intervention. And this is accelerating and helping the clinicians to make these decisions. More related to vascular aging, there are recently, not long ago, some works on plaq segmentation and characterization in the coronaries, in the carotid, in this case with OCT images, and they were doing also kind of an ex vivo validation, where they were applying kind of shallow algorithms after extracting some features, texture features, pixel positions. They were putting into random forest for classification, and they were obtaining kind of reasonable accuracies for fibrous tissue and lipid tissue, For calcified tissue, it was a bit less, but obviously, I mean, this is the wide regions here. It's very small regions, so this was quite tricky. It's quite a tricky task. This is another example using kind of deep learning, not shallow learning, but deep learning with kind of a large database also, also on OCT images, in this case of coronaries, and obtaining kind of better results than the previous algorithms. Well, kind of similar, around 0.I of dice. So this is one of the criteria. Maximum is 1. So giving reasonable results that obviously needs to be complemented with manual post-processing in case of errors. This is another one on ultrasound that obviously this is a very difficult task to work on B-mode ultrasound because of the noise. And well, you can see here in this case, a classical unit with no interaction. I mean, to have here a dice of 0.5 is not very good, but they found that by having some kind of interaction, given some input, manual input, like defining a region of interest around the plaq, that was helping a lot the algorithm and going to values around 0.8. That was quite good. There was on a large database also of 100 stenotic carotid plaque patients. In terms of echo, I mean, let's say that at the beginning, there were a lot of people working on high resolution images or like CTs, MR, and now people are starting to face more challenging imaging modalities like echo. There are nice databases like this one from Stanford that they're already open access. And this is just one group of them. This is a paper in Nature this year, Digital Medicine, where they train on more than 2 million 2D echo images from thousands of patients with kind of not basic, but well-known open source CNNs. Basically, they were trying to relate different indices with the images of pacemaker, the presence of pacemaker leads, more or less was working good, or to find if the left atria was dilated or the patient have an hypertrophic left ventricle. But you could see that there are other tasks like ejection fraction that were not good at all, like 0.5 of accuracy. This is not good. So a lot of work to be done in this type of images. If we switch to signals, I mean, we've been working on applying deep learning for signals, in particular ECGs, electrocardiograms, and we have discovered that this is even more difficult than working with images because of the large variability you have in signals and that you need very, very large databases. So we've been applying kind of some deep learning or developing new deep learning architectures to segment different parts of the ECGs, the Q wave, the R wave, the T wave, the P wave. So it's starting to work, and more related to vascular aging, it's something that, again, already in 2013, there were some works where they were applying classical MLN techniques based on pulse wave acquisitions with some on the carotid artery with some sensors. They were extracting some features of the signals and then putting onto this type of classifiers, random forest, different decision trees, Bayesian networks, and with quite good results out of it for classification distinguishing between hypertension and controls. A bit later, there were some works also to try to estimate blood pressure. In this case, using carotid waveforms that with tonometry recordings, they claim that it works with uncalibrated carotid waveforms. And basically, again, extracting signal featured from the recordings, integrated with clinical variables and with classical machine learning algorithms, and with reasonable accuracy as a good surrogate of pulse wave velocities. There is a really nice recent review of machine learning for PPG's signals, basically for the non-invasive complex measurements of blood pressures, and again, extracting a lot of different features from the signals and applying then machine learning for classification. more recent papers, what they are trying to do is to compare this feature-based machine learning with deep learning approaches where features are not imposed. And in fact, this is a recent work to predict vascular aging based on a smartphone acquired PPG signals. And in fact, these were the kind of covariates and the parameters that resulted after feature selection of all variables. And basically, they were finding that some parameters, some features like the second derivative of the PPG signals were the ones providing a very good classification when you were taking into account only two of these handcrafted feature from signals plus covariates. They were providing kind of areas under the curve similar to the CNN. So this is an example where you really don't need CNNs to provide similar characteristics and it's in this classification, or to predict the age of, aging and kind of a surrogate of healthy vascular aging. There are very interesting reviews recently in aging research, where basically they show that the deep neural networks, CNNs, you can input whatever data you want, and the label will be the age. And this can be done at multiple scales, basically at the macroscopic scale, but also at the more microscopic scale, depends on the features you want to extract. And obviously the applications can be multiple, from biomarker development just for developing markers, for aging, to compare different species, etc., etc. In fact, there is a lot of people working now on this biological aging, either from kind of, let's say, circulatory or hemodynamic markers, blood circulation markers, blood markers, to put onto DNNs with different populations. That was very interesting, this study, because it showed that if you train an algorithm with South Koreans, this is not going to work on Russian population or Canadian population. You need to integrate data from different populations. And also based on imaging. So you give an MR and then you predict the age. So there is a lot of work going on this type of works. And even you can use GANs just to generate images for all these. I mean, probably most of you have seen now that you can, in your mobile, from an image of yourself, know what you will be as old. But basically, this is GANs. It's a bit funny, I mean, this application, but it's just to predict this aging that you are going to have, okay? So let's move a bit to things that can be more interpretable. And this is quite important for healthcare. We've been working on this for some time, even for basic machine learning algorithms like decision trees. Again, just to see if we can better understand the data. You don't give labels to the data, or you don't give a lot of information to the algorithm. But then the important thing is when you have the results, how you interpret. And for instance, in this case, we built a decision tree out of a database for aortic stenosis risk stratification in order to predict the 6-year natural history of survival depending on the intervention. And what it was very, very interesting is just to see which parameters were used by the algorithm to do this stratification. And in fact, it gave us information that we didn't have. And these are the important things for interpretability. We have also tried to apply this with radiomics. Radiomics, it's basically extract a lot of different features from images and to put this into classical machine learning to see if we could use these radiomics features that they could be more interpretable. One of the problems, again, is data. How to find data that is not biased, that is not imbalanced, it's very difficult. And if you don't have this, it's very complicated to have a reproducible set of features. So there is a lot of work needed still to cope with this imbalance of data. Another type of unsupervised clustering that we have been used is kind of MKL, multiple kernel learning. And basically, again, it helps to generate or to input a lot of different data, in this case, echo data, but the different possibilities of echo, velocities, the formation, the V mode, the 4 chambers, and to integrate all this into a reference space, to build a reference space that is reduced in terms of dimensionality, and see if the algorithm managed to find different clusters out of the data, and to have kind of the spectrum going between healthy, the continuum between healthy and cardiac disease, and obviously between high risk and low risk. And again, the important thing is when you have this dimensionality reduction in spaces is, okay, analyze all these points. Each point is a patient, and then to see what's going on in these clusters, in this space, to see the parameters and try to see and relate them. This was done in a very nice work by Philippe Blancard and Barbinans in collaboration with Hospital Clinic, where basically using velocity and deformation echo data, it was to study hypertrophic cardiomyopathy and hypertensive patients. Okay, so this was again some individuals with family history, healthy controls, etc. And again, what I'm saying, the important thing was this regression part. So once we had this cluster, just to see what was going on with this data. And it was very interesting to see how LV remodeling and hypertrophy, it was associated with global and regional systolic impairment when we were looking at the data back at the strains, at different parts, etc. And basically what is interesting again is just to see how it works, this map. You can relate, in this case, the hypertrophic cardiomyopathy patients here in black with the HCM relatives that are a bit differentiated, but also with healthy controls that is on this kind of low risk side, and also with hypertensive control cohorts that were different. And then when, again, this regression is very important to identify these features that are important. And obviously, when a new patient comes, you project this patient into this reference space and see what's going on, okay? And you can define if it's in a high-risk region or not. We have done this to better understand complicated pathologies like heart failure, preserved ejection fraction, to predict the response of cardiac resynchronization therapy, which parameters identify better CRT responders versus non-CRT responders. And let's talk a bit about modeling, because modeling is very important for vascular aging, in particular models of the whole cardiovascular system. And in fact, what is starting to be the trend is to combine biophysical modeling with deep learning to take the most of these two kind of families of computational techniques. And we can use multi-scale modeling to impose prior knowledge into whatever is being done with machine learning. But at the same time, machine learning can help us an optimizer to identify the most important parameter values out of the database that we are working into, including virtual databases. We have been doing this in several applications, like in this one where we generated a virtual population of ECGs with patients with outflow tract ventricular arrhythmias. And basically, we were simulating ectopic foci in different parts of the ventricles. And then when the ECG of the patient arrived, we were comparing to our virtual population with machine learning techniques, and then to tell the clinician, okay, it looks like the ECG of this patient corresponds to the left ventricle or the right ventricle. So this was very useful. And the thing is, for virtual aging, we already have very nice models, 1D models, 0D models, 1D models, to generate virtual populations of arterial pulse waves, like in this work, recent work of the group of Jordi Alastray in King's College London, where basically we can simulate arterial pulse waves in almost the whole body. And this can be used to train algorithms, machine learning algorithms for vascular aging. And in fact, this group there are some Nokia guys in here. Last year and this year, they have presented exactly this. So running a 1D model of blood circulation, generating a large virtual database, varying different parameters, and then apply both kind of more Gaussian processing regression techniques or deep learning to predict cardiac indices. And obtaining reasonably good results for aortic pulse wave velocities. For blood pressures, a bit more tricky, not so good, and a stroke volume, but still quite interesting results. Other techniques, basically what they try to do is just to add to the machine learning constraints that fulfill the conservation of momentum and the conservation of mass that you know that biophysical modeling are going to fulfill. And basically you introduce this type of terms and this type of constraints and basically this helps to say you don't need to run the fluid simulations, but you only impose these constraints onto the what is called these physics-informed neural networks. And it's not clear if this is better or not, that biophysical models. There is a lot of work to be done yet comparing to the data, but in some cases it looks like it gives even better results than just the biophysical models. In terms of the structure, I mean, we have some works working on these handcraft 1D models of the vascular structure, but now more and more you start to see generative models like these GANs to generate the vasculature in any organ of the human body. So this is also coming. Here, in terms of simulations, I mean, we've been working on fluid simulations of the left atrial appendage to help on the optimization of device settings. And this is just showing that in this patient, we were generating, the device was implanted in a region where it could generate thrombus. And this is because it was there were regions with low velocities and kind of recirculation of flow, but obviously we need CFD simulations for this. So what we have been doing is just try to do this with deep learning. And basically it was to run a lot of CFD simulations and then try to learn the relation between the geometry and the outputs of the CFD simulation, that it can be a map of wall shear stress or whatever. And this is just results of this kind of wall shear stress maps. And the results are amazing because almost real time, the deep learning network were providing wall shear stresses very similar to the biophysical model. This combination of modeling and biophysical models is pushed also from agencies or regulatory bodies like the FDA in order to work with clinical trials, the new generation of clinical trials to generate digital evidence for this and have less experiments with animals, etc., and including this kind of deep learning. Okay, we have just had accepted a European project exactly on this, where machine learning and biophysical models will be part of it. So I'm going to skip because I'm running a bit out of time on the heart rate and connection part, but we are doing things, very interesting things on this side. But let me just finish with some important aspects on the system, software, and infrastructure. Okay, because in all this, obviously, I've said already that we are not going to replace clinicians. The AI is not only deep learning, the importance of interpretability, but also on the generalization of databases, data curation, and to have access to data in a secure, remote, and shareable way. And this is important, the data curation, because this is not usually the case. We need computational infrastructure in those hospitals in order to have large amounts of data that are properly maintained, and they need biomedical researchers in the hospitals to do this. It's not clinicians that they are going to do this, and be sure that we need to minimize missing information and uncertainty in the measure. We've been working a lot during the last years in the development of different platforms in order to generate, to read these databases, create front ends, backends, and to connect to deep learning so the clinicians can really have tools to process this data with AI. So I'm not going to enter in detail into these use cases. And also open access. We need to, this is very important for open science and reproducible research. And in fact, in imaging, we've seen a boom of medical imaging challenges like this this one I participated recently. Basically, you give to researchers open access data, and all of them trying to apply nowadays machine learning techniques for a given task, and then you compare all results. And this is very important to make the field advance collectively. Okay, federated learning is a way also to try to learn deep learning networks in each hospital so that the data doesn't need to get out of the hospital, and then it's only the network training that goes out and then is fused with other networks. So there are interesting initiatives on this. Cloud-based storage and management in the hospitals and in the universities are important also, and also generalization of the databases. We know that if you train a deep learning algorithm on images from whatever, from Siemens, and you apply it to General Electric images, this is not going to work. And this is very important, this generalization, okay? Open source software, again, super important. We have reached this point because open source softwares are open source and everyone can start not from scratch, okay? So just to finish, ML is not going to take over the vascular aging world. It's going to be very useful for well-defined tasks with good metrics and having large databases. It's not very good for reasoning, but still we can use together with humans and our reasoning to find and obtain new knowledge out of the data. And let me finish just about this paragraph from this recent review of Segers, because talking about how to measure arterial stiffness in human, I like it a lot what he was saying, how to be cautious. Like there will be a lot of kind of black box devices that will emerge for this kind of task to predict trends in pulse width velocities that will be trained on large data sets. But we need to be careful because basically they will translate and integrate it, whatever the data it has been trained on. And according to him, from a scientific technical point of view, they should be less useful for clinical practice and research than actual missions, because he thinks that they won't be able to detect the individuals who deviate out of this general trend. And basically, this is one of the most important things for AI these days.
Okay, here we are looking at the...
Oops, sorry. So again, basically, this is just another tool like physiological modeling, like new imaging modalities, like new visualization supports that we need to embrace and play with. So sorry for being a bit over time. Thanks to all my mates working on this, and I'm very happy to answer whatever questions you may have.
Thank you, Dr. Camara, for this interesting overview. It has been very informative. I was going to ask you regarding, because one of the main aim of VascageNet is to refine and harmonize estimation of stiffness, or in general vascular aging. So the question would be, how can machine learning and artificial intelligence be useful in the merging of population data from different centers, often different in terms of population included, analysis, interpretation of the data. So we will most likely include several databases in a larger analysis, and to understand how can we harmonize this data and include them all together in big population study. Can you comment on that?
Well, I mean, as I was saying, there are no more low-hanging fruits in the application of deep learning or machine learning in these types of data. And basically, what it has been done until now is just, okay, one big hospital or big center had a relatively large database, and this was provided, and then people were using only this database. And this has happened in a lot of countries, like for instance, in Alzheimer, everyone was using ADNI just to validate and set up their algorithms for neuroimaging. But in the end, you were working with a very biased database of white American rich people. And this is not reality. This is not a real world in every hospital or in every research. So nowadays, what is important is just to make the algorithms more robust, to work with data from different centers, from different populations. This is called sometimes domain shift, transfer learning. There are a lot of different names that you can have. Basically, I think you can use unsupervised learning to identify which are the features that separate these two populations. In one of the applications that I've shown too quickly, we were using this kind of MKL unsupervised clustering just to analyze kind of partogram data in women in emerging countries, just to predict the risk of having problems during pregnancy and during birth. And something very, very interesting is that the algorithm, one of the first things that pick up to differentiate the population was the country of origin. So without imposing the country of origin, the algorithm found that there were differences intrinsically in how the data was acquired in two different countries. So I think this can be important just to better understand the data. But you need to capture the variability that the existing variability that you have. Otherwise, I mean, the machine learning is going to fail because it's not going to invent this variability. Or you can set up this variability with virtual populations, but this is prior knowledge that you need to add into the algorithm. The effort on harmonization needs to be done by humans. I mean, it's kind of prior knowledge. It can be helped with some tools or not, but this is input that I think they need to be given on the algorithm, and for this it's very important to have standards.
Okay, thank you so much for this answer. In the interest of time, we will just make the one last question, sorry. So, as you said, we are acquiring and saving and having availability of a larger and larger database. And most often, research, search deeply into data or analyze in many different ways, and we end up with a number of parameters, potential biomarker, potential informative, even from a clinical perspective, which have some kind of shared information. So what is normally referred to as multicollinearity. In general, this poses a serious problem from the classical statistical analysis of this large database, and most often researchers choose, using what you call previous knowledge, which variable enter in this multivariable model, which will end up predicting or not the evolution of the patient. So what is, in your perspective, the improvement coming from artificial intelligence-based analysis in terms of feature selection or avoiding multicollinearity?
This is
why is that?
No, I don't know if it's better or not, but I think this is kind of a trending topic in machine learning these days and deep learning. And sometimes it's referred as disentanglement. Okay, and this disentanglement, what it means is basically, okay, we have some results based on some features, but let's try to see and to differentiate and see what is happened, what is the weight of each feature on the output of the deep learning technique, and see if we can, in the end, it's kind of doing some feature selection or some covariate analysis. It's trying to assess the effect of each individual feature of parameter and what is happening if you extract this feature or not. So in the end, you see in deep learning a lot of things that we have been dealing with in the classical methods that are starting to be important in deep learning. I don't know if it's better or not in the end. I think it's a combination. I mean, prior knowledge, it will be very important always, as in the classical methods, but maybe these algorithms to explore the data in an unsupervised way is going to help you to pick up these differences and these covariates in a different way, and just having better knowledge and new knowledge out of it.
Thank you so much, Professor Oscar Camara. In the interest of time, we will bring the webinar to a close. Thank you very much to everyone attending, and I will just say that this video will be available on YouTube and on a VascageNet website. It will be seen later on, and so we look forward to welcoming you in the next webinar, and thank you for Dr. Camara to spend time with us today.
Thank you, a pleasure. Take care.